friend, welcome to this third video of this Orange Piccolo printf. And today is gonna be probably the most difficult one because we have to handle integers. So we have to take into consideration all the flags. Major pain, right? I'm planning to do something bizarre, something hacky if you want. Let's jump into the code. Let's make a quick recap. So we have our Piccolo printf function. Here I just wrote some handy comments to make the code more digestible, more readable in GitHub. So we have the kicking of the variadic machine. Then we have our beautiful loop that is searching for the %, the sentinel of the printf. If this is not the case, we're just gonna stock inside 4K buffer the char. At the very end of the loop here, we're gonna flush all the thing, we're gonna clean up, and then we are gonna simply return the chars written. Cool. Now immediately I saw a little thing, which is this return -1, and it is not readable, right? It is like a magic number. Magic number simply means that it is something not tied to any immediate meaning. So this value is returned when init data returns me back true, right? And this happens when I have a malloc error. So indeed, I can immediately change here. If init data, it means that I have a malloc error. I immediately understand what is going on. If the init data fails, it means that it is a malloc error. And this is just a symbolic representation for this number. Negative because the printf, the real printf, is going to return me back a negative value if something went bad. Cool. So today we're going to increase the number of data that we can print. So we jump into the render format function, which is just here at the top, a wrapper function, right? A wrapper function that is going to call all the necessary functions to write in standard output the actual data type. So we are here on next video. So let's understand what we have to do now. We have digit and I, that stands for integer. Then we have, of course, pointer, lowercase x, uppercase x, and u for unsigned. These are the specifiers that we need to decipher today. And I will do this in a weird way. The thing is that I want to call just one simple function. So if I do something like, if our beautiful function in, then we pass this string literal, so the ipxxu specifier, you enter inside this conditional block. Here at the very top, you are gonna fetch the data. So this is gonna be step 1. Step 2 is gonna be call one king function for all. So I want to handle all of these specifiers only with one function that I can call, for example, print int, all right, something like that. Now, what am I thinking about? So I prepared these little slides to let you understand what is going on, or why it's going to be super cryptic. So we have the specifiers d and I, right, digit or integer, which basically are assigned int, right, data type. Then I have a x upper x and u, that stands for unsigned int, and then I have p, right, which is basically an unsigned long, right? A pointer at the end of the day. What is that? Well, it is just an unsigned long. The thing I want to do is that I want to have a king function, if you want, a king, that is able to print whatever integer. I don't really care about the size. And this function has to be able to print the actual integer in whatever base. Okay, so that's what I'm thinking about. You know that we have data types, right? We have char, int, we have float, double, and then we have with the qualifiers a short or a long. But at the very end of the day, if we go deep down inside the machine, inside the RAM, we can have only integer and reals, right? This is what is going on. The real difference between an integer and a real is the encoding scheme, right? Because an integer has the choose complement representation. On the contrary, real data types, such as float and double, have the scientific notation encoding, in which we have an exponent, an mantissa, You know this stuff, right? So we have a qualitatively different kind of encoding. So this is what is really different between an integer and a float. What is the point I'm trying to make? Well, the point is that at the very end of the day, a long, int, short, char are exactly the same thing. They are integers. The only thing that changes is the size, right? In this view, a char is a 1-byte integer and the long is an 8 bytes integer. It really depends by the machine, but much probably you're working on a 64 bits machine. So I can leverage this. I can leverage the fact that memory-wise, RAM-wise, a char is basically a 1-byte integer and a long is an 8 bytes integer. What do I mean? Well, I have that d and I are an integer, a signed integer if you want. Of course, we can omit this, it's going to be exactly the same, but to be pedantic. Then I have p, which is a pointer, namely a void pointer, namely a generic pointer like that, but at the end of the day, it's just an unsigned long, right? Then we have x, upper x, and unsigned. All of these are just an unsigned int, right? Now, why x and upper x is an unsigned int? Let me show you. If we launch this code, namely we want to print in hexadecimal the number 42, the integer 42, we are gonna get 2a, right? But if I do, for example, here, minus 42, what is going to happen in your opinion? Let me run this. I don't get minus with the symbol 2a, but I get this hexadecimal representation, which is the choose complement representation of minus 42. To be clear, let's make a simpler example. Here I put minus 1. Let you know that is always all the bits turn on in a choose complement encoding, right? So if I launch this, what do I get? Well, I will get all f. Namely, I'm going to get 8f, right? I get 2f are going to be 1 byte, right? Because one hexadecimal symbol is going to represent one nibble, namely 4 bits. And yeah, this is a 4 bytes integer. So you see that we are not getting minus 1. You see, we are not getting, for example, here, if I have 10, we are not getting minus a, right? But we are getting this big boy. So you see that we lose the concept of the sign when we are dealing with x, as well as with the octal representation. If I do here octal and I pass minus 42, let's say 42 beforehand, so the value is going to be 52, right? 5 per 8 plus 2, okay? So it's going to be 52, but if I say minus 42, I get a big boy. You see? Because this is just the binary representation of a negative. So we can basically consider these 3 elements exactly the same, namely an unsigned int. Okay? Now, what can I do here? Well, I can very simply promote this to a long, right? This is an unsigned long, so it's going to be the same, like that. And unsigned int as well can be an unsigned long, like that. I will promote the integer, and as well I will promote this. So now I have to engineer the thing in such a way that I can stock a long or an unsigned long in the same container, in the same object if you want. Namely, here if I do if in the or I specifier, you have to call va_arg, right? You pass data AP, and the type is going to be integer, right? Here we are dealing with the size, so the data type is going to be int. I cannot here put a long, right? I don't want to fetch a long because originally this is an int that eventually is going to be promoted to a long. And where do I stock this value? In the same vibe, I can say if p is equal to specifier, we are dealing with a pointer. Again, I will copy this, but this time I will fetch pointer, so void star, that I will cast into an unsigned long here, like that. Now the thing is that, where do I put this? Here, I'm gonna cast to a long. I will make a point, so don't worry. Everything will fit in the puzzle as long as we are doing this. So to stock this unsigned long And long, I'm gonna use a data type that probably you've never used, which is an union. An union is a fancy kind of struct, if you want, but contrary to structs, all the variables which are inside this union live in the same space in memory. This is pretty badass when you're doing embedded programming because you can save a lot of space. So when you have constraints, memory-wise, space-wise, it's pretty handy. You don't see very often these unions because they're quirky, if you want, just because they have this behavior. But you know, all these characteristics can be a plus or a minus. It really depends by the context. And in my context, it is pretty handy because I can do something that now I will show you. So in this slide, I have this union data type that I called onion, so you can remember this bullshit. And you have inside this onion two integer 8 type, which are basically one char, right? A signed char and an unsigned char. So let's do something practical so you can understand where I'm going. Okay, we are on C tutor, and as you can see, I have my onion here, data type. And here I'm declaring in the main an instance of this data type and assign the value -1 to n, right, which is the signed char. So here you have the beautiful visualization that we're going to change to byte level view of data. So you can immediately clearly see that we have the same address here. So n signed char and unsigned char live exactly in the same spot in memory. Bizarre, right? So let's run the code. I assign -1 accessing the signed value. What is going to happen? Next, boom. I get exactly the same binary configuration, of course, because we are dealing with the same space in memory. So assigning a value to n is going to spark as a byproduct also the changing of un, right? So here I get -1. Of course, these series of ones are perceived like assigned value, namely -1. But if I perceive these ones as an unsigned, this value is 255, totally different. All right. Then I call my function print value and I pass true. Basically, print value is a function that takes an union and a boolean to check if the number actually is negative. In the case if negative is gonna put a minus, right, in some output, and it's gonna invert the actual value. So let's see what is going on. This time the value is negative, so we have to perceive this series of ones as a negative value. We're gonna put a negative. So you can see here the negative sign, right? Then we perform the inversion. So I'm gonna say onion.n, accessing the signed thing, the signed because if the value is negative, I'm sure this is a signed value, and I'm gonna invert minus on.n, right? What is going to happen here? Next, I'm gonna get a 1, right? A normal 1, because inverting simply means flipping the bits and adding 1 in a choose complement encoding. Then I'm gonna simply print the unsigned representation of the number. Okay. So I click next, my function is gonna print, I go back in main, and I have -1, perfect. Now, what's the point of all of that? Now I assign to my union the value 200. This value is not gonna fit inside a signed char, right? Because it's too big. So let's click next and let's watch what is going to happen inside my union. Next, so I get here in my signed value -56. Of course, I have an overflow. I cannot represent with 7 bits this value. So I cannot have assigned plus 200 in a char, in a signed char. I hope you understand this point. On the contrary, in my unsigned, I get 200. No problem. This is totally representable. I can have till 255, right? So I call my print value again, passing this time false as an input. Next, we go here. It is not negative, so you just directly print the value, okay? And you get 200. So what is the point I'm trying to make here? How can I leverage this union to fit my needs, right? In my code, in my printf? Well, basically, I can have a union in which I will stock unsigned long, unsigned long, and I will pass this union to my print int function. Of course, I need also a flag to keep track if the value was negative. If it was the case, I can simply do the inversion and read everything as an unsigned. So you can see that with this union, I bypass the concept of signed or unsigned. All right, let's just code this. Eventually, while I'm doing stuff, this will become clearer and clearer because this is a knacky way of doing things. So back to the code. In my header file, I'm gonna create this union. So let's do here. Okay, stuff to use only one function for all ints. I'm gonna say typedef union, and inside we're gonna put an unsigned long that I can call uint64 and a long int64. We call this union int ack. Make it clear that this is something bizarre. All right, now in my render format, I'm gonna declare this, so union int ack, and the name is gonna be int values. Okay, something like that. Maybe I can put it close to the actual thing, make it more readable, and I say int values dot int64 is equal to 0. This is just initialize to 0 union. So now you understand that if I access int64, I'm actually also accessing unsigned int64, right? They're in the same place in memory, and they also have the same size, 8 bytes. So I zero this struct, this union, sorry. All right, so now I'm gonna stock inside my union. So here I have a long, I'm gonna say int values dot int64, right? Because this is a long. So I don't have any type problem. This is a long, that's perfect, right? The only thing I have to do also is just to save more information, right? Because I want to do this Aki thing. So save more info. Here in my header file, I'm gonna put, for example, a Boolean, like signed value, and a Boolean is negative, like that. So here I say stock in this value. I'm gonna set by default, so I can do data format signed value equal true, and I say if int values dot int64 minor than 0, you do data format is negative is equal to true. Okay, so I have all the information that is going to be handy lately. Then we pass to the pointer. So this is an unsigned. I'm going to simply say int values dot unsigned int64, like that. Here, of course, let me change to an else if. Else if. Now we have this string, which is going to be x upper x and u for unsigned specifier. Of course, I forgot to put in. All right. In this case, what do we do? Well, we are gonna simply fetch int values dot uint64 is equal to var data ap. Type this time is gonna be unsigned int, right? Unsigned int, like that. And by default, signed value is gonna be false because everything is zeroed every time I go into the parser, as well as this flag is gonna be also by default. So that's everything that I need to do, as well for pointer. So that's it basically. Right, so the first step is this one. Fetch the data and stock in Aki union. All right, when I have a digit, I also save more information like it's negative. So printint, my magical printint, now we are gonna pass the data, of course, and then we're gonna pass our beautiful union, which is int values. All right, so to recap, let's understand when I wanna go. I created this union to contain all integers, essentially. When I talk about integers, I'm not talking about int. I'm talking about char, short, int, and long. Signed or unsigned. Whatever value, whatever int can be stored inside this union. If I have d or I have a signed integer. So I'm gonna, first of all, fetch the actual integer, then promote to a long. I cannot fetch as a long here, right? I don't want to fetch 8 bytes. I just want to fetch 4 bytes and then just simply perform the promotion. So I won't lose any data. And then I'm going to save some more information, basically that the data is signed, and if it is minor than 0, it is actually negative. If I have a pointer, this is basically an unsigned log. I will fetch as a void star, and then I will cast to an unsigned log. Perfect. Then the flag signed is going to be false, because by default every time it's going to be refreshed to 0, and is negative as well is going to be false. And then x and unsigned are going to fetch as an unsigned int, and then I will, here I forgot to perform the actual casting, make the code more correct, even though it works the same. Unsigned long, like that. And then you just call printint, then now we are gonna implement. This is a badass function that is able to render inside the buffer what we need. All right, let's create, we have render char, render string. Let's create a file that I call render int, like that. As usual, we include at the top our orange printf. Now let's do this king function. So king foo able to render whatever int in whatever base, in buffer obviously. So let's do void print int, the usual pointer to data, and then we have our union. We pass this ACKI object here, so it's gonna be union int ACK, int values. Here it comes. We are gonna simply pass by value. We don't actually care about passing by reference. Perfect. Now let's deconstruct the algorithm I'm thinking about. Now inside my union, I have a value, right? I have a value, I have an integer value. It can be signed or unsigned, but at the end of the day, it's just gonna be a value. For example, if I have a D and I specifier, I can have the value signed 1992 or the negative counterpart. The thing I want to do is to call a function, an itoa base function, so an integer to alpha function able to write in whatever base, and stock the actual string representation in a temporary buffer that can be 64 bytes, totally enough. So as you can see, I will stock only the actual digits. I will forget about the sign. I really don't care, because I have the flag that is telling me if the number is negative in the case or if it is positive. If I have x or unsigned, I will have a value, an integer value, and I have to convert in x hexadecimal representation. In this case, it's going to be cafe 42. This is an hexadecimal value, yeah. And I'm going to stock in this temporary buffer as well as for a pointer. A pointer is just a very big value, right? An unsigned long. And I will convert in its hexadecimal representation in the temporary buffer. After that, I will have inside this temporary buffer the actual thing that I need. Then I will only to process the actual spaces, padding spaces, zeros, the sign, and so forth. Here inside this temporary buffer, I just want the clean value representation in the base that I need. So let's write some pseudocode here. First of all, let's assume I have this integer value. Just write alpha of it into TMP buffer. So I will need a function that I call itoa base that takes as an input data an int value. Let's do values because we have signed and unsigned. So clear that. All right, to do. Then the second step is gonna find out spaces, namely padding spaces and padding zeros, and do a function set padding zeros. As always, pass data. On the same vibe, set padding spaces. That. Third step, just write in buffer the number. Of course, now we have to pay attention about justification. So if data format dot left justified or less. So if it is left justified or not, so else. So this is kind of the blueprint of my print int. Now let's start by the itoa base. Or a better naming would be itoa, maybe buffer only to make it short. Itoa buffer, integer to alpha into buffer. And we assume that we have also the base embedded. So here in my header, we are gonna just put utils, a temporary buffer. That's it's gonna be char buffer tmp. Let's say 64, like that. So just a little buffer in which I'm gonna write the alpha representation of the number. Then let me put also the actual cursor of this temporary buffer in the same vibe of the bigger buffer. There's gonna be simply, well, it's gonna be number len, right? This is gonna be pretty useful later when we're gonna deal with the precision and stuff. To know the number len is fairly useful. So let me write just the MP buffer converter, MP buffer index. Make it clear, if I have 2a, which is 42 in x, number len would be here, it would be 0, right? Where is 2? 1, and then 2. So I have number len is 2. Pretty handy, right? So here we have, so the buffer and the index that is going to act like the actual number len. Perfect. So ito a buffer now. Let's go to our buffer model. And now we have to make this badass function. So we have a function to convert all integers, unsigned integer, namely long, but with int I imply the encoding scheme, into a string. So void ito buffer. As an input we are taking pointer to data, like always, and our union int ac. So this is going to be int values. All right, first of all, we do the actual control, check base. So we say if data format dot base is minor than true, right? Or the base is major than 16, we simply return in our implementation. We can also do bigger bases. We just need more symbols, so we can create something really funky. Now, the thing I want to do is recursion. So this is going to be complicated to explain. This is going to be like a put number recursive. I made a video already. Maybe you can check in the description. I will leave a link in which we are going to put inside the buffer the this is crazy to explain, frankly. Basically, we're going to do a put number base recursive. So this is bizarre, right? It's start to be kind of cryptic. Maybe I will write the code and then I will explain. So inside the recursion, check if the number is negative. Then we have 2 base case. 3 is going to be recursive case. Okay, so here maybe we can put a 0. First of all, check if the number is negative. How do I do that? Well, simply I will do if data format is negative. What do you do? Well, it is implied that the value is assigned one, right? If it is negative. So I can say int values dot int 64 is equal to minus the same. Simple inversion. So int values dot int 64, basically inverse. So now I have a positive value. I recall to you that we are inside the union, so pay attention to that. It is important. Then I simply recall again. So I to a buffer, data, and I pass int values now with the converted value. Easy, right? So now let's do the base case, which is going to be else if. Now I have to check if the value is less than the actual base. So I'm going to do int values. And now we have only unsigned, right? Because I always convert the thing. I don't care. I always convert. If it is negative, I will convert to a positive representation. So every value I will get as an unsigned. So I will take the unsigned is minor this time than data format base, right? Which is a value ranging from 2 to 16. If this is the case, what do you do? Well, you have to stock in the buffer the actual symbol. But here you have to pay attention also to in the uppercase or lowercase. We have to check if we have the flag uppercase or lowercase for X and upper X, right? We can have this or this. So if data format dot uppercase, we put data format dot temporary buffer in position data format number len, right? Then we increase with plus plus is equal to what? Is equal to what? Well, here in my other file, I'm gonna put my symbols. So I will do something like that. Define symbols, and then I put the symbols that I need. They're gonna be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. I will copy this and I will make this time uppercase. So A, B, C, D, E, F. So let me change these to lower symbols and upper symbols in fashion. Okay. If it is uppercase, upper symbols in position, the same position as the value. So int values dot unsigned int 64. This is what is going on. Pretty convoluted, but we'll make it work. Else, exactly same thing. So we are gonna pass this and we're gonna simply change here to lower symbols. Okay, so this is the base case. Namely, if the value is minor than the actual base, for example, if we have a base 10, if you have a value ranging from 0 to 9, we're going to put the relative symbol inside the buffer. Okay, let's do the actual recursion. Well, recursion here, else, is going to be a little tricky. The thing is that I want to divide and then use modulo to the actual unsigned value. So to do that, I will need a temporary variable. Let me write. So union int ac that I call tmp, and I say here at the bottom, tmp unsigned int is equal to what? Is equal to int values unsigned int, I always access unsigned, divided the actual base, so data format dot base, like that. And then I call the recursion again. So itoa buffer data, but this time I will pass the temporary, so tmp. I do the same, so I simply copy this, but this time it's going to be modulo, replace modulo, and again I call the recursion. Boom, itoa buffer. All right, that's basically it for this recursion, I guess. So don't be fooled by the weirdness of this. It's pretty easy. Basically, it's put number recursive, itoa base. I made a video about that, itoa base. I will leave a link somewhere so maybe you can understand better what is going on here. But basically, we have a check for a negative value. If it is negative, call again the recursion. This time is going to be positive. Now, the problem is that this is a flag. It's going to be always true. So data format is negative. It's going to always be true, even though I change to a positive. So I need another flag, basically something like that. And let me put here in my header is negative, boolean is converted. Let's put boolean is converted. And here we do something like this. We convert, we say data format is converted is equal to true, right? Because now we made the conversion. And here we enter this block only if data format dot is converted, and we negate, and data is not converted. So here is written, hey, if the number is negative and has not already been converted, just enter here, do the conversion, the flag is converted, and itoa buffer again, so you launch the recursion. That's basically what is going on. Then here we simply have the base case in which we check if the integer value is basically is less than the actual base, and then we index inside the symbols, which are basically just a string, a defined string, uppercase or lowercase. So we simply check the flag here, and this is the recursion. It's just divide and modulo, and I will use a temporary union because the weirdness of the union itself. So make sure you understand how a union works. So basically, this is my itoa buffer. This is a function that is able to stock in my buffer whatever integer in whatever base. And the thing is that after this point, everything to me is unsigned. Everything from here is read as unsigned. So all the union gimmick is just a thing to have one single function, which is itoa buffer for signed and unsigned values. Otherwise, I had to write a very similar recursion, a very similar function for both cases, which is not elegant. Maybe more readable, but not elegant. And you want to write as less code as possible. All right, so let's just copy this itoa buffer in my header here. All right, like that. So we have this badass function now available. And if we go back to render int, now we have itoa buffer. So After this call, I have in my temporary buffer the string representation of my int, signed or unsigned or whatever. Okay, that's already a good leap. Now, for integers, we have to take care about plus, space, 0, hash for hexadecimal, and of course minus, right? All the flags, of course, we have to take care about width, and of course about precision. So now I have inside my temporary buffer the string that I need, but I need to find out how many spaces and how many zeros given the string, and having also the number len, how long this string is fairly useful for this purpose. So first of all, we're gonna get the number of zeros that I need to use to pad my string, right? My 1192 string. What is the idea here? Well, the thing is that the spaces are in function of the number of padding zeros. And the number of zeros derived by 3 factors. The most important one is precision. We'll show you a clear example. Then the zero flag, and of course the number len. These are the actors that are gonna discipline the number of zeros that we're gonna have. I say precision is the king. Let me show you why. So if I have the number 42 and I say precision of 10, what is going to happen? Well, I have all these padding zeros, as you can see, right? If I have 42 and precision of 4 and a 0 flag here, what do you think? What will I get? And of course, let me also put a width of 10. So I have 10 width, 0 pad, and 4 precision. This is what I get, my friend. So here I wrote 2 times D. Never mind. Let me launch again. And you get this. So you get 4 2 padding zeros, right? And you do get all the padding here, even though I have this 0 pad flag. So precision is pretty important. Gonna be the first thing to watch. If I remove the precision here, I will get, of course, all padding of zeros. And so this padding really depends by the number len, and then of course also depends by the fact that I can have a sign, right? I can have a plus. So if I run the test, I have 1 0 less. So these are important things to keep into consideration. So set padding zeros and set padding spaces. First of all, I want to set the actual zeros because the spaces are in function of the zeros. So here the sequentiality as a logic. So let's make a file that I call format utils, visual inclusion, like that. Perfect. We're gonna do zeros to pad. Okay. Spaces are in function of zeros. So I will count zeros before end. All right, something like that. So it's gonna be void set padding zeros, type data, pointer data, like this. So we have that precision is the king regarding the zeros. So precision is the king of zeros. In my buffer, so tmp buffer tmp, I have the string representation of the integer. So for example, I have this one without a sign. So if this is negative, I will know only with the flag, right? Flag is negative. Here I have only the representation. And here I have the index, right? Which is basically number len. Number len is equal to 4, which is basically the index we are using in the temporary buffer. Cool. These are the ingredients that we have. So check if we have a precision thing. So I do if data format precision value is major or equal than 0. Basically here the question I'm doing, is there a precision? Question mark. If it is major or equal than 0, what do you do? So you have to check if the precision is bigger than number len. In our case, is bigger than this, 1992. So if data format precision is major than data format number len. You understand what I'm doing? Basically, here if I have this inside the buffer and the precision is equal to, I don't know, 6, this is an indication that you have to pad with 2 zeros, right? 2 zeros. So it's gonna be 0, 0, like that. So very simply, inside this block, you're gonna put data, format. Here I need a variable that I call padding zeros. So let me do that. It's gonna be here int padding zeros. Okay, so now let's do that. Padding zeros is equal to what? Well, is equal to precision. So data format dot precision minus, I go on the next line, minus what? Well, data format number len, right? So the number of zeros is going to be true in our Silo example, right? If I have number len 4, precision is going to be 6. I will have to pad with 2 zeros. And given that this is precision, namely the most important, let's say, value in our format, we are going to simply return done. Done. So return. We have faithfully managed to set the number of zeros that we need. Done. Okay. So here we are in no precision length. Here I'm sure I don't have a precision, so I have to check the other flags. So let's check if I have a 0 pad in this case. So if data format 0 pad, if this is the case, so namely if we have the actual 0 flag here, because this is the other case by which we can have the 0 padding, right? What do? Well, immediately you assume that if you have a left justified, this doesn't make any sense. This is an undefined behavior and this is wrong. So you can say if data format left justified, you simply return. Doesn't make any sense. You have padding with left justified. So you put here something like wrong input or undefined input. Cool. You can see that as long as we are coding, we are removing complexity into simple, manageable chunks. Now, I care about the space, right? If we have a positive value and we have also this flag. And of course, the width, right, is very important because the 0 padding happens when we have a width major than number len. So let me do initially something like that. If data format dot width is major than number len, so data format dot number len, format number len. If this is the case, what is going on? Well, we're going to have data format padding zeros, which is equal to what? The width. So we're going to fetch minus number len. You see? For example, if I have a width of 10, right? And here we are in no precision length, so I don't have precision. The number of zeros by now, so let me remove this. Here in this section, we only do width, is going to be 1, 2, 3, 4, 5, 6, and then the number, like that, you see? So padding zeros is going to be width minus number len, which is going to be 10 minus 4. So in this case, the zeros are going to be 10 minus 4, which is number len, equals 6 zeros, right? We are not finished, of course. Now, we have to check for eventual signs, right? Plus or minus, or even space, frankly, or space. So we have di p x upper x u. And we also have to check for 0x, frankly. So, or 0x for hexadecimal. So x, pointer, integer, digit, all of these can have symbols, but the unsigned doesn't care at all about symbols. So we can simply say if data format specifier is equal to unsigned, we are done with this padding. So we're simply return. On the contrary, else if in, let's do x upper x specifier. So if we have an hexadecimal and here data and we have format hash, right? If we have the actual hash flag, talk about this. So let's put into parentheses, or what is the other condition? Or the specifier is a pointer, so data format specifier is equal to p. Well, what do you do in this case? Well, you have to remove 2 padding zeros, right? Because we have to pad with 0x. So data padding zeros minus equal to, because 0x bad, right? Other case, the actual signs. So let's do minus. Let's do here else if again. The number is negative, but here in X there is another thing that now I called. What is that thing? Well, basically, if you have like a number like this one, X, and it is 0, so if you do 0, you run, you don't get the actual 0x indeed. On the contrary, if you have something different from 0, you're gonna get 0x, perfect. So here we have to put another end. It's gonna be data format into temporary buffer in position 0 is different from the char 0, right? Because now it is a string. Perfect. So now if the data format is negative, or the data is positive, so we can simply say not negative. So data format not is negative, and we inverted logic. And here we have to do data, we have the plus flag or the space flag, right? So data format space. All right. So we have, if the number is negative or the number is not negative, namely positive, and we have a flag plus or a flag space, well, it means that I need to put a sign, right? So let me remove data format padding zeros minus equal 1, or very simply minus minus, same. And we are done, right? With our beautiful function. Here at the very top, I just do a safety control, namely if data format padding zeros is minor than 0, just set it to 0. So data format padding zeros is equal to 0. All right, so we have our padding zeros function. I think this is not too terribly complicated. As you can see, the logic is split into a precision or a not precision, and inside the actual non-precision land, you have to take care about all the possible flags and possible combinations. All right, tac, here I just put safety control like that. So we know exactly how many zeros we have to put for our custom integer. Now we have to make the other one, which is set number of spaces. So this is going to be very similar. So void set padding spaces, and you get a pointer to actual data. So we already have the zeros from the previous function. Before I was telling you that these spaces are in function of the zeros. So remove the zeros. Remove zeros. So you do something like spaces. So are equal to the width. So format the width minus now the zeros. So data format zeros, padding zeros, and of course minus the actual number len. So data format number len. Makes sense. We can have, for example, width 10. So it's going to be 1, 2, 3, 4, 5, 6, the number. But here, if I have precision 5, means that I need a 0 here. And I know this value from the previous function. Padding 0 is this one, it's going to be 1. Number len is going to be 4. 4 plus 1 equals 5. So I get padding spaces by now, at the very beginning, is going to be 5. But we have to process everything. We have to process also the other flags. So you can see immediately why I need the padding zeros call beforehand. So you say, if we have this specifier, namely unsigned x or pointer, if this is the case, what do you do? Well, we simply have to copy this piece of code here for the hash. So let's copy that. Indeed, it is bad practice to write the same piece of code twice, but I don't want really to make this overly convoluted and too much centralized, which already is. So I have to tell if these are the flags to write data form. This time I have to remove not the zeros, but the spaces for the same logic as before, because I have to use 0x. And then basically that's it. You can return like that. Of course, here is easily expandable with other bases. For example, 0b or for octal 0. You got the point, right? So here, game done, right? I simply do return because we are done with unsigned x and b. On the contrary, I have d and I, so I have to take into account plus space and if it is negative, right? So let's do that. So if the number is negative, it's negative, what do? You simply data format spaces minus minus for the negative sign and you return. Game done. So here let's just put a minus. We're gonna handle minus sign, positive sign. So it is not mandatory, so we do if data actually is positive, format I use this negative converted. So if the number is not negative and what? And data format plus, right? We need the flag. We do the same as before, so we copy these 2 lines. We pass here to be extremely verbose, but to make a point, I will simply copy this. Better, I will copy everything because I want to keep it simple. So if the number is positive and I have a space, right? The code is going to be exactly the same. I want to show you all the steps. You understand what I'm doing, right? I'm checking all the possible combinations that there can be. So now I have these 2 beautiful functions. I will copy, set padding space and set padding zeros here, like that. All right, so let's go back to my render integer. Now we are done. Because basically I have the number written inside my temporary buffer. I know how many zeros and spaces, and now I just have to write inside our output the actual number. So if it is left justified, first of all, I have to think about the sign. It can be a sign to write. After the sign, the zeros, right? There can be zeros. Then third point, the actual number, and then potential spaces, right? That there can be. On the contrary, if it is not left justified, it's just an ordering issue, right? So first of all, you will have the spaces at the very top. Then you will have the sign. Then you will have the 0 and the actual number, like that. All right, let's, as usual, divide and conquer this thing. Now, for the zeros, I will simply call my function put char buffer n. The char is going to be a 0. Precision is going to be data format padding zeros. And then I simply pass data. Done. So I will simply copy these also here. For the actual number, I will use put str buffer precision, or buffer n. The string is going to be in the temporary buffer, so data format temporary buffer. Here I'm going to put the len of the string, so data format number len. And then, of course, I'm going to pass the data normally. And for the spaces, I'm going to use put char buffer n. This time I'm going to change here to the space. And here I just put padding spaces as the precision, right? And data. Okay, now let me copy this here and this here, like that. Now we need a sign to write. Okay, so let's make a static function that is going to live here. So let's do static void put sign. For sign, of course, I mean an umbrella term that can be 0x, can be minus, can be plus, can be 0b for binary or 0 for octal. You got the point, right? Something on those lines. So type data. Okay. So we're going to copy in our format utils this logic as before, which is this one, right? Here, yank, and pass here. So if we have an hexadecimal and hash, and it's different from 0, or it is a pointer, you have to put 0x, right? But first of all, we are going to check the uppercase. So again, nested condition. If format uppercase, you call put string buffer precision, which is going to be uppercase, so 0x, precision 2, and data. Else, just copy this and put lowercase, so 0x, like that. Here, to make it simpler, I can do something like this. I can do if data format base equal to base 16. You're gonna call a function doing all this jazz that I will call put 0x as an input. I give data. Okay, so let's do very briefly, copy all this, and let's do void put 0x data, and we simply pass all of this. Okay, of course we're gonna do it static like that. Nice. So now we can simply remove all of this. Here we say if is base 16, you put that 0x if this is the case. Else if data format, we use this time the flag is signed, namely is gonna be signed value, as we can see here. What do you do? So we have simply to check if the data is negative. So data format negative. You put a char in the buffer. So put char buffer and it's going to be a -1 and data. Else if the data is positive, so not negative, data format is negative, not. Then we have to check if, as you can see, it's a plethora of if nested one into each other, the printf thing. So if data format plus, you put a char buffer n and you put a plus. No? Precision is going to be 1 and data. Else if, and this time we have to check not data plus, right? Format dot plus and data format space. So we have to check if we have the space and the plus flag is not turned on. We simply copy this code, paste here, and we put a space here. All right, it's done. Yes. So we have this function put sign that now we can use inside my render int, print int, namely, put here at the top, put sign data here and also here. Okay, are we done? Namely, the blueprint, it's done. So let's try to make some tests now. I'm just gonna copy this print int here to the render functions. All right, let's go back to the printf.c and now let's check. Print int has been done. Now let's go in my main and let's try to run some tests so we can see the bugs. Okay, here I just made with ChatGPT a lot of tests that now we are gonna launch. Okay, let's launch. All right, here we have the test for int. Immediately a mistake. I miss completely the number. It's not being written in stdio out. Something is missing. Something big is missing. All right, here immediately in my ITO buffer, I see this word glitch. I don't know why I have that. Probably did I do that mistake? Weird. Okay, let's cancel this because I think probably some auto-completion stuff kicked in. I don't know. Okay, let's just try with that simple correction. Already better. So let's go to integers. All right, we start to get the integers that we want. The charts are equal, and you can see that we start to get exactly the same output, right? For every case, even in those weird cases. All right, we have big input, weird stuff, 4,125 with a space at the very top. Right, these are other tests. Everything seems legit, right? We're unsigned, all the padding for pointers. It seems that everything works properly. All right, so we managed to do this model, if you want, this integers model. We are basically did something like that. And I want to emphasize that we can do it even something more. For example, we can increase the number of our specifiers. For example, we can put a B, stands for binary, which by the way, the normal printf doesn't have. So now let's simply do some changes. We go in the parser and we add the binary here. So we say else if data B is equal to specifier, so data format specifier. We set the base to base 2, so data format base equal to base 2, like that. So this is a new feature. There is not in the real printf. New feature. All right, so we track the binary. Then we go into the printf.c and we say if in, we have to add the actual b, and we're gonna fetch as an unsigned int. So we add here b. Okay, so we have the int fetched, then our render int. Well, probably we have to put a 0b just in front of to make the binary thing. Let's try to launch that. So let's go in the main and let's make a very simple test to see if it works properly. Piccolo printf. We're gonna do %b this time, and then we pass, I don't know, for that. Let's see what we get. So we compile and launch, and as you can see here at the very bottom, we get our beautiful binary 101010. All right, my friend, we are done with this printf trilogy. If you want that I do another video in which I'm gonna do the full thing with new features, like as you saw with the binary and with the other bases and something bizarre that you think it's cool, well, just let me know in the comments. I will push this on GitHub, allegedly bug-free, but you know, this is an open source, quote-unquote open source thing. We are doing this all together, so it would be marvelous to get comments, feedback, improvements, and so on. All right, thank you for watching, my friend. Enjoy.